Good morning, students. My presentation on Fermat's theorem, Wilson theorem, and problems on it. Before going to that, I introduce some basic definitions related to these theorems and problems on it. The first one, set of all integers. We know all of you the numbers are in the form of 0 plus or minus 1 plus or minus 2 and so on is called an integer, and it is denoted by capital Z or capital I, and P is the prime numbers 2, 3, 5, 7, 11, 13 and so on. Suppose two integers A and B, they are not equal to 0 or said to be relatively prime. Whenever GCD of these two numbers must be 1. And one more, congruence. Suppose A and B are two integers and M is a fixed positive integer, then A congruent B under modulo M if and only if M divides A minus B. Note, if P is a prime and A comma B are two integers, then P divides the product of A and B. This implies P divides A or P divides B. Now we are going to prove the theorem. The first one, Fermat's theorem. The statement is, let P be a prime number and A be any integer not divisible by P. Then A power P minus 1 congruent to 1 mod P. Now proof of this, consider the complete set of residues modulo P, that is 0, 1, 2, 3 etc. P minus 1. Now you call it as equation number 1. Then the set of integers, that means each term of equation 1 is multiplied by the element A, that is 0 into A, comma 1 into A etc. etc. The last one P minus 1 into A, I call it as equation number 2, also form a complete set of residues. Hence, each integer in equation 2 is congruent to just one integer in equation 1. Since 0 occurs in both equation 1 and 2, each integer in the set, that means we will cancel 0 equation 1 as well as in equation 2. The remaining, the set 1 into A, comma 2 into A, etc. P minus A is congruent to just one of the integer in 1, comma 2, etc. etc. P minus 1 under modulo P. Therefore, A comma 2A, comma 3A, etc. P minus A, this is congruent to 1, 2, 3, etc. P minus 1. So here in left hand side of this equation, A will repeat P minus 1 times. That's why if I take A power P minus 1 as a common factor, the remaining is 1, 2, 3, etc. P minus A. This is congruent to again 1, 2, 3, etc. P minus 1. Now in this equation 1, 2, 3, etc. P minus 1, it is nothing but P minus factorial. This is congruent again, this is P minus 1 factorial under the modulo P. On cancelling P minus 1 on both sides, we get the required equation A power P minus 1 congruent to 1 mod P. This completes the proof of theorem. So on the basis, the corollary of the above theorem is, if P is a prime, then A power P congruent to A mod P for any integer A. Since A and P are relatively prime, that means GCD of A comma P is equal to 1. So on the basis of by Fermat's theorem, A power P minus 1 congruent to A mod P. On multiplying both sides by A, we get A power P minus 1 into A equals A modulo P. Now if you simplify the left hand side of this, A power minus 1 into a power 1, that is minus 1 plus 1 will cancel. The remaining is a power p. This is congruent to a mod p. This completes the proof. So on the basis of this corollary, we can take some example. Let p equals 3 and a equals 2. Now we apply again once again by the Fermat's theorem. A power p, that is 2 power 3, that is congruent to 2 modulo 3. That means 2 power 3, that is 8. Under modulo 3, the remaining residue is 2, which is true. And one more, let p equals 7, a equals 3. Once again on the basis of this Fermat's theorem, a power p, that is 3 power 7, congruent a means 3 under modulo 7, that means 3 power 7, that is 2187. This is congruent to 3 under modulo 7, which is true. Next, we go to Wilson theorem. The statement, if p is a prime, then p minus 1 congruent to minus 1 mod p. Otherwise, if I take this minus 1 into left hand side, it p minus 1 factorial plus 1 congruent to 0 mod p. Now we go to proof. When p equals 2, that is the first prime, p equals 2, then 2 minus 1 congruent to minus 1 modulo p, mod 2. 2 minus 1, that is 1, that is 1 factor. This is congruent to minus 1 mod p. Otherwise, if I take 1 factor means 1, when minus 1 become to left hand side, that is 1 plus 1, that is 2. 2 congruent to 0 modulo 2, which is true. That means 2 divides 2, the remainder is 0. In generally, let a be any integer such that 1 less than or equal to a less than or equal to p minus 1. Since p being a prime, a and b are relatively prime, consider the linear congruence ax congruent to 1 mod p has a solution a inverse which is unique. Since a comma p is equal to 1, that means relatively prime, therefore a into a inverse, this is congruent to 1 mod p, has a for minus 1, it is lies between 1 and p minus 1. Suppose a inverse is equal to a, in equation 1 we get a into a congruent to 1 mod p. A into a, that means a square, it is also congruent to modulo p. So by note number, on the basis by using the definition of the congruence, p divides a square minus 1. Otherwise, p divides a plus 1 a minus 1. That is, we are applying here a square minus b square formula. On the basis, this a square minus 1 will be split into 2 factors, that is a plus 1 into a minus 1. So again, once again by note number 1, so p divides this product, otherwise this implies p divides a plus 1, otherwise p divides a minus 1. Also, since the value, the integer a lies between 1 and p minus 1, it follows that a plus 1 equals 0, otherwise a minus 1 is equal to 0. Hence, a inverse is equal to a only when a equals p minus 1. That means a, when minus plus 1 become right hand side, that become minus 1. Otherwise, a minus 1 is equal to 0, otherwise a equals 1. Therefore, 1 and p minus 1 are the only self-inverse element in ZP. ZP means set of all integers, we are looking only prime numbers. Hence, the remaining elements 2, 3, 4, etc. p minus 2, that means the previous element of p minus 1, which are p minus 3 in number, can be paired into p minus 3 by 2 pairs of integers of the type a inverse, where a into a inverse, this is congruent to 1 modulo p, but a inverse not equal to a. Therefore, 2, 3, 4, etc. p minus 2 congruent to 1 mod p. On multiplying, otherwise the same thing we can also write 1, 2, 3, etc. p minus 2. This is congruent to modulo p. We call it as 2. Also, p minus 1, it is congruent to minus 1 mod p. we call it as equation 3, which is true for all p. So we can also verify this condition by taking for some particular values of prime numbers on the basis equation 3 is always true. On multiplying equation 2 and 3, we get 1, 2, 3, etc. p minus 2, p minus 1 factorial minus 1 mod p. Therefore, 1, this repeated instead of 1, 2, 3, etc. p minus 2, p minus 1, we can write p minus 1 factorial. The right hand side part is as it is minus 1 modulo p. Otherwise, when it minus 1 becomes left hand side, that is plus 1. Therefore, p minus 1 factorial plus 1 congruent to 0 mod p. This completes the proof. For example, to illustrate the p minus 3 by 2 factorial, for that I can take an example. P equals 7. It is possible to divide the integers 2, 3, 4, 5 into p minus 3 by 2. That means here p is equal to 7. 7 minus 3 by 2. 7 minus 3, that is 4 by 2. 4 by 2, that is 2 pairs. Each product of which is congruent to modulo 7. Therefore, the pairs are, that means 2, 4, that is 8. This is congruent to 1 under modulo 7. And one more 3, 5, that is 15. This is congruent to 1 under modulo 7. On multiplying these congruents, which gives, that means 2, 3, 4, 5, their product, it is also congruent to 1 modulo 7. Otherwise 2, 3, 4, 5, it is nothing but 5 factorial. This is always 1 under modulo 7. On multiplying both sides by 6, we get 2, 3, 4, 5, 6. This is congruent to 6 modulo 7. Otherwise, this is 6 factorial. 6 can be written as minus 1 under modulo 7. Therefore, 6 is minus 1 under modulo 7. Thus, p minus 1 factorial congruent to minus 1 modulo p with p equals 7. That is 6 factorial congruence to minus 1 modulo 7. Problem on the basis of this: show that 18 factorial plus 1 congruent to 0 modulo 19. And one more, 18 factorial plus 1 congruent to 0 modulo 23. Or if you combine these two problems, 18 factorial plus 1 congruent to 0 mod of 437. Proof of this: here 437 means we can write number of product of primes, that is 19 and 23. Since 19 is a prime, by Wilson theorem, 19 minus 1 factorial plus 1 congruent to 0 modulo 19. That is 18 factorial plus 1 congruent to 0 modulo 19. We call it as 1. That means which proves 1. Again, 23 is a prime. Again by Wilson theorem, 23 minus 1 plus 1 congruent to 0 modulo 23. 23 minus 1, that is 22 factorial. This 22 factorial can be written as 22, 21, 21, 20, 19, 18 factorial. Now we can stop up to 18 factorial plus 1 as it is congruent to 0 mod 23. Now 22 can be written as minus 1 under 23. Again 21 can be written as minus 2 under 23 and so on. 19 can be written as minus 4, 20 can be written as minus 3 under the same modulo 23 and plus 1 as it is. Again, if I multiply all these negative numbers, here we are looking 1, 2, 3, 4 negatives that become positive. Again 1 into 2 into 3 into 4, that is 24. Therefore 24 into 18 factorial plus 1 congruent to 0 mod 23. Again 24 can be written as 23 plus 1 into 18 factorial plus 1 congruent to 0 modulo 23. Now we can split into two terms. 23 into 18 factorial plus 1 term. Again plus 18 plus 1, it is another term congruent to 0 modulo 23. But 23 under modulo 23, it is always 0. Therefore 0 into 18 factorial, it is always become 0. Therefore only remaining 18 factorial plus 1 congruent to 0 mod 23, call it as equation number 2. From 1 and 2, that means if I combine the equation 1 and 2, finally we get 18 factorial plus 1 congruent to 0 mod of 437, because equation 1 is says that 18 factorial plus 1 congruent to 0 modulo 19. In equation 2, the same thing modulo 23, therefore 19 into 23, that becomes 437. So on the basis of the Wilson theorem, we can also take one more problem. Show that 712 factorial plus 1 congruent to 0 mod 719. As per the above procedure, we can apply and solve, we can get the required result. Thank you.